Welcome to The Explainer. Today, we're going to put on our detective hats and dig into one of the most powerful tools out there for making decisions with data: statistical testing.
All right, here's our game plan for today. First, we'll look at the kind of questions that need a data detective. Then, we'll meet the main suspects in any statistical investigation. We'll also talk about the risks of getting it wrong before we walk through the entire six-step process, from the first clue all the way to the final verdict.
You know, we all have questions. Some are huge, some are small, but they can only really be answered by looking at the data. The real trick, though, is how do you go from just a hunch to a decision you can actually be confident in?
I mean, take a question like this. This is a big one. A simple guess just isn't going to cut it. When people's health is on the line, right, you need a totally solid way to figure out if a new treatment is really doing what it's supposed to.
For example, an organization like the FDA might set a very specific bar. They need hard proof that a vaccine is effective, say better than 30% efficacy, before they can even think about approving it.
Or, think about a factory manager. Maybe they've just spent a ton of money on new machines. They have to know, is this thing actually faster? Is it shaving off a meaningful amount of time, like a full minute from production?
It even applies to something like this. A pet food company wants to know if dogs genuinely prefer their new salmon recipe over the old chicken one. See, these aren't simple yes or no questions. They all need a formal process so we don't make a big, costly mistake. And that whole process, it's called hypothesis testing.
So let's get into the heart of how this works. And honestly, the best way to think about it is like a courtroom trial. Except instead of putting a person on trial, we're putting an idea on the stand.
So, every single statistical trial starts with a suspect. We call this the null hypothesis. This is basically the default setting, the status quo. It's the assumption that nothing has changed, that there's no new effect. Just like in a courtroom, it's our innocent until proven guilty.
This slide really breaks down that central conflict. Over on the left, you have the null hypothesis. That's the world as we know it, where nothing has changed. The vaccine efficacy is still just 30%. Dogs don't care what they eat. But on the right, you've got the challenger. That's the alternative hypothesis. This is the prosecution's case. It's the new, exciting claim we want to test, that the vaccine is better, that dogs do have a preference.
And this is a really crucial point. We never actually prove that our new idea is right. Instead, we're using data as evidence to see if we can confidently throw out the old idea. The whole goal is to show that the status quo, the null hypothesis, is just so unlikely based on the data we collected that we have no choice but to reject it.
Okay, but before we even look at a single piece of data, good detective work means we have to think about what happens if we get it wrong. And in statistics, there are two big ways we can mess up the verdict.
The old story of the boy who cried wolf is actually a perfect way to think about this. When the boy yells wolf and there's no wolf, that's what we call a type 1 error. It's a false alarm. But later, when the wolf is real and nobody listens, that's a type 2 error, a missed danger. In any test we run, we're risking one of those two mistakes. So here are the official names for those mistakes. A type 1 error is raising that false alarm. A type 2 error is missing a real threat. And as the person running the test, you have to decide ahead of time which of these two mistakes is the worst one to make for your specific situation.
So, now that we understand the risks, how do we actually do this? Well, it's not just a guessing game. It follows a super clear 6-step playbook. Let's walk through it.
This is it. This is our 6-step process. First, you state the status quo and the new claim. Then, you decide how high the bar for evidence is going to be. That's called the significance level. After that, you collect your data and boil it down to one number. You draw the line in the sand for a guilty verdict, and then, finally, you make the call.
Now, step 4 here is absolutely the key, the test statistic. It takes all your data, which could be hundreds or thousands of data points, and crunches it down into one single number. This number is basically the strength of the evidence against the status quo. It tells you just how surprising your result would be if the null hypothesis were actually true.
Okay, don't let the scary-looking formula here throw you off. A lot of the time, we use something called a z-statistic. The easiest way to think of it is just as a ruler. It measures how many steps away our result is from what we expected to see. The bigger the z-score, the further away we are, and the more surprising and powerful our evidence is.
And that brings us to the moment of truth. Before we even run the test, we draw a line in the sand. We define this rejection region. You can think of it as the guilty zone. If our evidence, that test statistic, is strong enough to cross that line and fall into this shaded area,
then we can declare that we have enough evidence to reject the null hypothesis.
Okay, all this theory is great, but let's make it real. Let's take that 6-step playbook and put it into action with a classic example, a political poll.
So here's the situation. A candidate's support was sitting at 50%. Their team goes out and polls 100 new people, and now 60 of them say they're on board. That's a 10-point jump. But the big question is that a real increase, or did they just get lucky with their sample? So we set it up. The null hypothesis is that nothing's changed. Support is still 50%. The alternative is that support has actually gone up. And we're going to set a really high bar for evidence. We'll only accept a 1% risk of a false alarm.
All right, time to process the evidence. We take our poll result, 60 out of 100. We run it through the formula, and boom, we get a Z statistic of 2.0. This single number, 2.0, that's our entire case. That's the strength of our evidence against the idea that nothing has changed. So here it is, the verdict. Because we set that super strict 1% significance level, our guilty zone, that rejection region, doesn't even start until a Z statistic of 2.33. Our evidence, a Z-score of 2.0, is pretty strong, but it's not strong enough. It doesn't cross the line. So we have to conclude that we can't reject the null hypothesis. We just don't have enough evidence to confidently say that the candidate's support has gone up.
So let's just step back for a second and look at the big picture here. This whole process, this kind of structured skepticism, it's not just for scientists. It's a really powerful way of thinking for anyone who has to make decisions when they don't have all the answers.
So, what have we learned? Hypothesis testing is an amazing tool. It gives us a structured way to challenge the status quo with evidence, and it protects us from getting fooled by just random luck. But that leaves us with one last really important question. In our example, we didn't find a significant result. But what if we had? What if we'd found a tiny 0.1% increase that was statistically significant? Would that actually matter in the real world? And that's the ultimate challenge, right? Moving beyond what's just statistically significant to find out what's truly meaningful. That's the difference between a detective who just closes the case and one who really understands what the verdict means for everyone outside the courtroom.